Hello everyone, and in this video we are going to look at the app that you will be using to do the computations for this practical. It's called MolCalc or Beta MolCalc, and I've listed it here, the link for you in the practical guide, so you just need to click on that. And then the page should load that looks something like this. Okay, so the first step in what you do in Beta MolCalc is you need to draw the molecule that you are looking at. It has some predefined molecules for you, so like methane, there it is. You can click on benzene, then it forms it for you. Then there's a water dimer, you'll be using this, but these two are your most important ones. So let's start with the methane. Then you have several different atoms, because remember, the molecular mechanics are restricted to certain elements. And these are the elements that it is basically restricted to. And let's say, for example, so if you want to add an element, then you just need to click on it, and you click on whichever element you would like to replace. That one, that one, that one, that one. Okay. This is not a molecule that exists, but just to get the idea of what you want to do. If you want to replace something, just as I did with the hydrogens there, you can replace it. You see it immediately updates the valence for you. And you can also, this optimize button, after you've drawn something, you can click optimize. And then you see there's this little bit vibration, and there's this functionality turned a bit. What the optimize does is it tries to find an energy minimum for your structure or your molecule that you've drawn. Just some general other things, you can zoom in on the molecule by scrolling back on your mouse, or you can scroll out. Same thing. If you click somewhere with the left mouse key and you drag, you can rotate the molecule. Okay. Then you can also assign different bond types. You can also break bonds if you would like, but for our purposes, mostly we'll look at just different kinds of bonds. So let's say, for example, we want to make this a double bond. Now you see there's 5 atoms there, 5 bonds on the carbon, which is incorrect. And I will get to the issues or problem solving now. So for example, you can't do any calculations on this, but just for the illustrative purposes. If you just want to delete everything, then you can just click on methane again. It takes you back. So let's say, for example, we want to build, so let's go to carbon, and then we want to build propane. You can do it in the 3D editor. Just zoom out a bit. But there's also a 2D version if this is easier for you to work with. So once again, we can start with methane, and then you can just do that. You can also then start by adding different, what's the word I'm looking for? Different kinds of stereochemistry you can add, etc. If you would like to do that. I like the 3D version because you can see what is there. So you can switch between the two, but you can use whichever functionality you would like. And then, of course, double, single, triple bonds. And yeah, then in terms of deleting certain bonds. So let's say, for example, you want to draw something like carbon monoxide. Okay, so carbon monoxide has a triple bond here and doesn't have a hydrogen there. You click here on the erase, just erase the hydrogen. But now notice there's a problem with our valence, right? Because carbon needs 4 bonds, oxygen only needs 2 bonds. So that is what these plus and minuses are for here. So now the carbon is negatively charged. You can see there's a -1 there on the carbon, and our oxygen is positively charged. You can see there's a positive charge on the oxygen then. So this is how you can make radicals as well when you need. Or let's say, for example, you need to look at a different molecule that is very similar to this one, then you can look at it. Also, again, you see after I've clicked somewhere, it immediately changed the molecule because it will optimize on its own as well. But that's important. So you need to optimize before you do anything else. So once you're happy with what you've drawn and you've figured out the valences or whatever, if you haven't figured out the valences, I promise it's going to complain. So then you know there's some valence issue. All the structures I asked you to draw, you can draw. And it shouldn't give you any problems. Okay. So now let's just draw something that's going to give us some interesting results. Well, not interesting, but yes, methane, for example. Now we say we want to calculate properties. It's going to ask you, are you ready? So not yet. Let's say, for example, you press it by accident. You can change back, calculate properties. You say, indeed, it's going to take you to a new page. And you need to stay on this page. So you see, there are 4 options there. Don't go to new molecule. New molecule is going to erase the calculation you just completed. So now you're on this page, and this is your results. So firstly, free energies, some thermodynamics. Here you can see there's your Gibbs free energy, there's some enthalpy data it has, heat capacity, entropy. So anything you would like to look up of this specific molecule. For this practical, you'll be focusing on perhaps on this part more than the entropy and the heat capacity. Also, if someone would like to attempt to explain where this translation or rotation or vibrational thing comes from, you're more than welcome to do that as well. But anyway, that's just a side note. Yeah, so you have a page that gives you then molecular orbitals. So in 385, you made molecular orbitals and you looked at them and whatever. And what I want to show you now is how. So you just did it for diatomic molecules, right? You didn't really do it for polyatomic molecules. So for example, you're going to have to look at benzene and triene and a few other things, and you won't be able to figure out those molecular orbitals by hand in the way you did for 385. So that's where this comes in. You can visualize them. So if you click on it, then you can see this is how the molecular orbital looks like. This, for example, if I had to classify, so you see that's the 1s orbital of the carbon, mainly contributing to the lowest energy molecular orbital. And then this one is probably a combination of the S and all the S of the hydrogens. This one is out of phase, so these ones are all in phase. This is out of phase, and you might say this looks like a P, so it's probably a P orbital from the carbon. Again, a P orbital from the carbon, just different. And you see they're all similar in energy here, so they all should look kind of the same. And then all of these are again the same, similar in energy, but some of them are difficult to classify. I'll take that. I mean, what on earth is that? Well, I mean, I can guess S orbital, S orbital, S orbital, P orbital, if I had to guess. And you can go through that. You'll see important aspects later on. Most importantly, the last minus and the first plus, that's what we call the HOMO-LUMO gap. So this is the HOMO, highest occupied molecular orbital. This is the LUMO, lowest unoccupied molecular orbital, in case you were wondering. And then finally, it gives us also some information on polarity and solvation. So, for example, you can see this is a very green molecule, so it means it's extremely non-polar. You can also see that in these values. You can see its solvation energy in non-polar solvents is much higher than it is in polar solvents. And also there's no dipole. Important. You're also going to use that later on. So if you need to compare solubilities or see things like that, you go to this tab. Okay, and as I said, if you're going to press the new molecule button, it's going to take you back to this page, and then you're going to have to say calculate properties again to get back to this page. Not that it takes forever, but you know, if you're busy with something, just don't do that. Just a last note on the polarity one, I forgot. You can put on the dipole moment, and then if it has a dipole, it will show you. So let me quickly just draw something that has a dipole, like methanol. We say yes. Now you see the colors have changed, right? There's a clear one there, and if we put on the dipole, then you can see there's a nice arrow indicating the dipole is in that direction for you. In a different way than what you would expect. Most of you probably would have said the dipole lies there, not like that. Okay, so that's in general what I wanted to do with this. So you can play around a bit. I mean, it's very user-friendly, and if you make mistakes, just draw the molecule here and just calculate again. You know, don't worry too much. This is more just to show you that there are powerful things out there.
Okay, so let's also talk about the assignment that you have to now complete for this. So you've now been introduced to beta MolCalc, and you've realized it's an absolutely beautiful little tool that you can use thanks to the University of Copenhagen. And you're now going to test the limits of it in different questions. And you will notice that in each of these questions, I give you a mark indication, but I just give you some general ideas and I give you hints and I tell you to actually just discuss something. Also give you some guidance at specific questions. There's some video instructions that you can watch to guide you further in it, as well as some additional theory that you can read for each of these questions. And depending on the complexity of the question, the more information I provide or the more guidance I give, etc. But it's not really based in a typical way that you would have asked or that you would ask questions. It's more based in a way of a philosophical way that you should approach chemistry. In that, I want to see what you come up with. If someone were to ask you to argue these questions, so if someone were to corner you in a street alley and ask you in the middle of the night, you need to argue this or they're going to stab you, how would you go about that? You know, how would you save your life if your life depended on the argument that you're going to come up with? That's what I want to see. So there are right answers, of course, so there are things that are right, but there are different ways in arguing them. So even if you only provide one of them, there are actually three different ways that you might be able to argue the same to get to the same answer. Or you might get to different answers depending on the models that you use, the premise that you use to argue these. And that is what I'm interested in. I'm interested in seeing how the 3 years you spend at varsity has culminated in you as a 382 student, and your abilities have now brought you to a stage where you are able to argue and logically explain what you want to say. So that's why this assignment is not based on specific questions. I give you something to discuss, and I want to see how you interpret it, and I want to see the level of effort that you put in. That's what I want to see. So I'm not really interested in the answer that you get. I'm interested in seeing your logic. And that's how the memorandum is set up. Actually, there isn't a memorandum. And it sounds weird, but memorandum is all in my head, usually. And I give some guidance if we have markers, if I don't mark myself. That's how it works. So specifically for this practical, it's all about how you approach it. It's not about what you think the answer is. It's not about what you want the answer to be. It's about how you are going to approach it, how you're going to argue it, and how you're going to use the tools provided to you and your chemistry knowledge. Everything that you've learned, not just in this course, everything that you've learned over the past 3 years needs to be applied here. So it's actually much more difficult than it might seem on paper because I'm expecting a lot of you. But you're a third year student in your final semester, and it should be something that you would enjoy. You should enjoy the challenge. Otherwise, you're at the wrong place. Okay, so that's the assignment. I hope it makes a lot of sense. Of course, um, it's 100 marks, and this 10 marks will only be given there at the end, which says overall completion, plagiarism, and impression. That is really for the level of effort, your editorial care, and of course, plagiarism in terms of what you provide us with. You really need to prove that you deserve to get 10 marks here. As well as there's a 3 mark bonus for the general feedback, which I would like you to give on the entire course, not just this experiment, but the entire course in general, if you would not mind. If you don't want to answer it, you're more than welcome to leave it blank. If you would like to answer it, then there is 3 bonus marks, which you can obtain for that. Okay, that's everything for the computational practical. I wish you all the best of luck, and please use all the video materials and the practical guide. I think everything is really well explained. If something is not well explained, for example, like this question, 5.1, 5.5.1, It's a challenge question, so you're not really allowed to ask any additional questions. I want to see what you come up with. Again, we're testing your knowledge. We're trying to find out what can you do. Okay, so good luck.